Okay, hopefully it will.
Hopefully it doesn't crash my system.
Well, let's hope. Anyway, so we're happy to have Anton Mellit from the University of Vienna. Is it correct? Are you at the university? Yeah?
Yes.
Okay, and he will speak about P equal W via H2. So it looks like a secret code, so you should explain.
Yes.
Okay, go ahead.
So the title is P equals W via H2, right? Can you read what I'm writing?
Yes.
So I have to explain what is P, what is W, and what is H2 first, right? So let's start with from left to right. So by the way, can someone use the camera? Have a camera on, because otherwise I don't know if I'm talking to anyone or not.
Well, you're fine so far.
Okay, this is better. Thank you. Yeah. So the main object is a moduli space of this moduli space of local systems, which is also moduli space of Higgs bundles. So on this side, we are parameterizing somehow. So it's actually twisted moduli space. So we fix the following data. We fix G and N and D, so R and D. And G gives us a Riemann surface of genus G. R gives us rank, and D is another number, will be the degree. And the twisted moduli space is you let sigma prime to be sigma G minus a point, and you want to look at representations. So a set of representations of the fundamental group to GL R C, such that, well, here we have our Riemann surface, and this is our point, and there is a little loop gamma, such that, so, and these are our homomorphisms, such that phi of gamma equals e to z2 pi I over R times D, and times the identity matrix of prime R. And this we parameterize up to conjugation. That's one moduli space.
So this is the left-hand side, because yes. I really do not understand, because what you describe, it's an M Betti, it's not equal to M Dalbo. It's not equal.
This is very well known moduli space, and yes.
Well, it's maybe very well known to some people, but maybe some other means different things. For example, you wrote equality, which is incorrect. So maybe you understand it in different way than I do. Yeah.
I didn't say what is the other side, and I didn't say what it means that they're equal. So
okay.
Let's
equal means equal.
With the right-hand side. The right-hand side is the moduli space. This is the set of, now sigma is algebraic curve, and we are looking at stable Higgs bundles of rank R, degree D. And yeah, I forgot to say that R and D are supposed to be assumed to be relatively prime. And this is, so what is a Higgs bundle? Bundle is a pair, call it E and theta, where E is a vector bundle. Okay, let's bundle on the curve, and theta is a map from E to E twisted by the canonical line bundle. And stability means that there is no Higgs subbundle of larger slope, and this is so as usual. Now, right. So, what is the relationship between these two moduli spaces? And this is given by so-called non-abelian Hodge correspondence. So non-abelian Hodge theorem tells you that gives you a bijection between points of these two moduli spaces. Implicit bijection between MB and M.O. And then, which is this bijection is continuous, but not complex analytic. Okay, so that's the meaning of the equality here.
So maybe you comment, because I see some graduate students here. You see, if there are two sets, infinite set, there might be many bijections. So when you say that non-abelian Hodge theory gives you a bijection, you mean some particular bijection?
Yes, there is some particular bijection. It turned out to be continuous, but not complex analytic.
Well, in fact, it's diffeomorphism, but but maybe you kind of explain what is it, because one is a pure topological thing, the other depends on the complex structure. So it's kind of, it can happen that they are equivalent, but in what sense? Can you say it quickly, or we should believe it as in the black box?
So we will use it as a black box. We never need to actually use it But if you want to have an idea about how to construct it, if you start from the left-hand side, you have a local system. Then you have to prove that your local system has certain nice metric on it. And then you can use that metric. So existence of this metric is some kind of optimization problem. And then once you have that metric, then you can use it to twist the trivial complex structure on your local system to obtain a Higgs bundle. That's roughly what it is. And going backwards, it's the same. If you have a Higgs bundle, there is some optimization problem you need to solve to find a metric. And then using that metric, you can twist the complex structure on your bundle and get a local system. So you get a flat connection, so you get a local system. That's basically. Is it sufficient? Adequate?
Yeah, probably it's sufficient if there will be no further question. Again, it's just for the sake of the audience.
Yeah. So, but now, so these two spaces are. So one example, maybe one example in some trivial situations. The left-hand side would be something like C star times C star. And the right-hand side is elliptic curve times C. That's sort of to give an idea of how these two spaces can be related topologically, as topologically they are clearly the same space, but completely different from the point of view of algebraic geometry. Yeah. So what do we do with these spaces? So again, and this is yeah. So we know abstractly that cohomology of MB should be equal to the cohomology of what we are that above isomorphism, and we want to understand different structures on the cohomology ring. One structure coming from its realization as a MB, and another structure coming from its realization as M dolmo. So it's some rings. Yeah, so there are some rings, and we want to understand the extra structures. And on
you take cohomology with a rational.
Or complex coefficient.
Complex. Okay.
So on B we have so-called Betti filtration. And on the other side,
not on B, but on cohomology would be.
Yeah, on cohomology. Betti filtration, and I will draw a picture after this. And on the other side, we have so-called perverse filtration, which I'm going to explain. And the equal W conjecture will tell you that Pi equals W2I, and this is by Hausel, Cataldo, and Migliorini. And let's start a new page to explain what it means. Okay, what is it? So let's start. By the way, how much time do I have? I forgot to ask.
Well, you have an hour plus something for discussion and other things. Yes. Yeah.
So let me try to explain how these two filtrations how they look like. So,
and Anton, before you start to explain, you wrote something that one kind of is equal to the other one, but you said that your diffeomorphism of two spaces is very, very special. It's something which comes from the black box, from this non-abelian Hodge theory. So when you say that one is mapped to another one, you mean just this very specific diffeomorphism. If I change it, then okay. So then whatever you will prove should rely on this very special diffeomorphism.
Right.
Okay.
Right. So now some more information. So here is one theorem that is usually attributed to Markman, but okay. So the theorem is that this ring that we are looking at is generated by tautological classes. And so what are these tautological classes? So let's consider. So our moduli problem, it parameterizes some sort of bundles on the moduli space, and in both situations we have something like a universal bundle on. So this is a bundle on the moduli space where M is ME or M1 times your surface sigma. So this and doing that,
I have a question.
Correspondence.
No, I have a question already here. Because on the Betti side, your sigma is just a topological surface. It doesn't have any structure. So I have no idea what do you mean saying that you have a universal bundle. Because your Betti, it's not an algebra, not an object of algebraic geometry as you defined it. Just representations of some fundamental group. Or do you mean something else? Or do you impose a complex structure on sigma?
Well, the problem is that it also so there is some complex vector bundle. Well, the problem is that this statement is not quite true, because what you actually have is a projective bundle, which has there is an abstraction to making it into a actual vector bundle.
But do you choose a complex structure on sigma when you speak about Betti side?
No. For this statement, I don't need complex structure.
Then I have no. Then I do not understand what's. So you say that there is some complex vector bundle E with cargo E.
It's not holomorphic,
okay.
right?
So then when you say that it's a universal, it does not mean that it's a universal in the sense of algebraic geometry. Okay.
Well, it sort of is in each situation, in each of the two situations. In Betti situation, you have the universal local system. I mean, it's not quite true as I'm saying, but it will take a little bit too much time to explain exactly what is true. But you can completely, for the purpose of the discussion, pretend that it is true. So it is such a local system on M times sigma, where if you restrict to a point of M, you get a local system on sigma, which exactly the one which you want to parameterize. So this gives you this universal bundle. And what you can do, because it's a complex bundle, you can take Chern classes. And in particular, you can form a Chern character, the total Chern character of E. And this is some series inside the, so it's in the cohomology of n times sigma. And, okay. If you take star here, you get 2 stars here. And what you have to do, you have to take, so the definition is as follows. So it's a bit non-standard. The psi star of psi. So here psi has to be an element in the cohomology ring of sigma, and you take this charm thingy, you cap it with psi, and then you push it forward along the projection to n. And I forgot, I need also the third class of sigma. Yeah. So if you like more explicitly, you have classes in the cohomology of the product m times sigma, and you can decompose it in unit decomposition, and this has some polynomials in those thingies. So in the unit components. So so if you define everything carefully, then there is a sequence of classes. You get a sequence of classes. Each class lives in H to K. Plus I minus 2, where I is in, if psi is in the cohomology, the I's cohomology of so this is the cohomology of M.
In I's cohomology of what?
Oh, sorry, of sigma. Yeah. Okay, so you take the Chern class. The K's Chern class is in H2K, then you multiply it by psi, and then you project it down, and that projection decreases the cohomological degree by 2, because sigma is 2-dimensional. Okay, so the theorem tells you that these classes generate the cohomology ring. And from this point of view, there is a theorem by Schende which tells you what is this weight filtration on the cohomology. So the W to W M monitoring is a span of all products of the form psi K1 of psi 1 and so on, psi K R, no, not R, sorry, K L, instance of psi L, so that here the sum of K i's is less or equal to 2 times the sum K I is less or equal to M. So in particular, only even values of m make correspond to some jumps in the filtration. And the rough idea of the proof if I equals 2 in xi, so xi means that xi is an H2 of sigma, then psi k of psi is H2k in the moduli space. And this corresponds to the fact that psi k itself is actually Chern class of some vector on M. So Chern class of a bundle on M, because psi corresponds to the class of a point. So you kind of, this corresponds to a point on your surface, and you're restricting your vector bundles to that point, and you get the bundle on the moduli space. So in this situation, the classes come from characteristic classes of an actual vector bundle. And if you remember that construction of characteristic classes, they come from maps to some Grassmannians. And Grassmannians are some smooth projective varieties. And classes which come by pullback from smooth projective varieties are called pure. And the weight filtration is precisely so that it kind of measures how far your classes are from pure. These are pure, and so the so in W2K, H2K, and the meaning of the W2K plus I of H2K are classes which are obtained by some from pure classes by some sort of shift by I. So if you just have used pullbacks, then there are no shifts. But if you're using some long exact sequences in cohomology, then it results into shifts. So that's the rough idea of the weight filtration. And in this theorem gives you precise gives it precisely. Okay, the weight filtration. Now I want to talk about the perverse side. Any questions for this statement? Anyone there still?
Yeah, go ahead. Yeah. So far it's, I mean, the weight filtration, it's an easy part.
Yeah,
it's easy to understand.
From this point of view, we think that weight filtration is something we understand well. Now let me explain perverse filtration. Now, this is more generally can be associated to a projective map of algebraic varieties. Map of, let's say, quasi-projective varieties. you say x over some base a, and so how do we understand this? How do we think about perverse filtration? So assume that A is also projective. Then let sorry. So if it's a projective variety, then we have an ample class. The cohomology of A, the ample, and let eta in H2 of X be also ample. And we also, yeah, so let's set up. Then you can look at, consider this map, let's call it phi. Consider phi of the star L. This is now an element in the cohomology of X, and we consider cap product with this element, and this is an operator, the important operator on the cohomology of X. If you so it's an important operator. It's can be completed to, so one way to say you can complete it to a SL2 triple and obtain a grading on the vector space. But of course, the grading will depend on the choice of the SL2 triple. So SL2 triple. But the filtration associated to that grading is independent of the SL2 triple. Grading and filtration, sometimes called monodromic filtration or monodromic filtration. And so you get some filtration. But this is not the perverse filtration. Filtration on X. And then call it, I don't know, call it M. I X. If you want to be precise, then it is unique filtration such that this operator L has a sense Mi to Mi minus 2, and so that Mi mod Mi minus 1 is isomorphically sent iterating to this. Unique determined by these properties. So this operator L has degree 2, and then the perverse filtration, and now I will make probably a mistake. sum of H, so it will be K, and there is some M, and so plus I think minus I. So I. So the idea is that by L should that should not change the filtration steps. So if it increases cohomological degree by 2 and decreases m by 2, so it preserves the result. But yeah, so this is the definition of perverse filtration.
You see, when you say that this is a definition, I have never seen this definition. Who made the definition and when?
Ah, I see. You want to be really picky about it. So yeah, so there is another definition using perverse shapes, and then there is a theorem by Cataldo and Migliorini that is the same filtration. But if we don't want to go into perverse shapes, we can accept this as a working definition. Sum over. Oh, this is key. Maybe I made mistakes. So this is how we understand the perverse filtration, and here are examples. And there are two opposite kind of examples. One example is when A is the point, then X is just the projective variety, and in this situation pk is just hk. H less or equal. Okay. So and the second situation
less or equal means sum of cohomology.
Yeah, take all the cohomology degrees less or equal. And if pi is identity, then after you adjust everything, then p is 0, p minus 1 is 0, and p0 is the whole cohomology. That's these are the two extreme cases. And crucial property of this filtration is this relative perverse. Which generalizes usual perverse in example 1, which and it goes as follows. So we used L, the ample class on A, to define some structure, and this structure now is nice with respect to eta. So the relative perverse says that eta to the appropriate power, which is k, from p minus k mod p minus k minus 1 to pk mod p minus 1 is isomorphic. So that's the story of the perverse filtration in general. Okay.
So I do not understand. In your definition of perverse filtration, eta did not appear at all.
It didn't. It's true, right? It's only
So now,
that.
so when you say relative hard Lefschetz, is it a statement or it's
Yes.
assumption of what?
Yes, this is a statement.
Ah, okay. So it's not an assumption.
No, yeah. I kind of
So you
from L and eta. I used L. I constructed a filtration, and then I claim that eta satisfies this property.
any ample class satisfy this property, because there can be many of them, yeah.
Yes, and indirectly, if you use different class L, the filtration is the same. So okay, now we have these two. So this was in the case of this was for x to y to a, where a is projected, and hence x is projected. So what do we want to apply this to different situations? So we consider take X to be the moduli space bone. Then it is well known that there is a map from X to vector space of dimension X over 2. So this sort of X has twice dimension as a base, and so it's called Hitchin map. Hitchin map. And the construction of this map goes as follows. If you have E and theta, which is a point here, you take the characteristic polynomial of theta. Now, theta is a matrix whose entries are differential forms locally. You take characteristic polynomial, you get some differential forms, quadratic forms, and so on. So if you what you obtain is this section. So this characteristic polynomial is a section of the direct sum from I equals to 1 to R of the cohomology of of the i's power of I. This is all happening on the curve. So this is some. This is what we is isomorphic to some vector space of some dimension. Turns out to be half dimension of X. So we want to apply the theory to this situation, and the problem is that A is not projective. But in this situation, we have a theorem that cohomology of X is pure. So here is the definition. Homology of X is pure for some, hence for all smooth compactifications. X inside this part is the map from the cohomology of a compactification to homology of X is surjective. For examples of spaces with pure cohomology is C. C to some power, for instance, some springified layers. Some of the spaces. Okay, and this and our space by the theorem. So then, because of the theorem and slightly a little bit more work, we can simply.
So, Anton, what's the statement? I do not understand. H star, the cohomology of X is pure if what? Or X, you mean Dalbo? Okay.
Definition. So then
I understand the definition, but what the theorem says?
That
cohomology of what? Of what? Of
M dot 1. The definition is that perverse filtration on this cohomology. So in this situation when it is pure, it just the filtration induced from the cohomology of a smooth compactification, so that such that bar is extension of the Hitchin map, which we call H, to any smooth compactifications. Projective. So this is what we work with. Yeah. So now let's as I explained what is a perverse filtration, I'm going to now formulate the results. So theorem. So this P equals W conjecture is true. False. And then, so there is some little story here that there are two proofs. Now, one by Mellit Shen, and another one by us. So, how's that? And this, so kind of independent proofs appeared both in September last year. And the first Mellit and Shen uploaded their proof, and then we had to kind of speed up and upload ours. So, so there are two proofs, and this one is some perverse sheaves. And then we'll talk about and some support theorem, support, and some other things. But our proof is somehow more about the cohomology. So extra structures. We discover an interesting and extra structure. Extra structure homology of the multi-space, and the structure turned out to be so useful that it, in particular, proved equal W conjecture. So, what is this extra structure? So this extra structure is this H2. So this H has nothing to do with the cohomology. Sorry if it confuses someone. What is this? It is the Lie algebra of Hamiltonian polynomial vector fields on C2. So explicitly it has basis corresponding to monomials into variables. So if you have a monomial xm, yn, we call denote by d and n. Then in this DMN, the bracket is like this. This is determinant m prime n minus n prime. So that's the Lie algebra, and our theorem is that so we have H2, and let me also throw in the homology ring of the curve. If we have any, so here, yeah. So this is the Lie algebra. Actually, super Lie algebra, because the ring is not commutative. So this acts on the homology of the moduli space. So that D0 n and the psi is x by the operator. Oh, sorry, I just one correction, but first I statement psi and psi, and I forgot that this here I need to introduce two more formal variables. Okay. And then plus some sort of explicit action with respect to x and y.
Plus what?
Yeah.
It's not clear. Psi and psi plus something.
Or something depending on x and y.
Ah.
Depending x and y. Some explicit. So so this is already. If I didn't say this last thing, then this is already some non-trivial statement. we have another thing is that dmn is the first plane, the second plane is a dmn psi sends some perversity pk to k plus n.
Sorry, what is dmn of psi?
Oh yeah, I meant this notation. This element, which I usually abbreviate dmn psi. So that's the. It's maybe more sound. So if you want to play with this statement, then the x is d01 of a point, y is d10 of a point, and so you can. So the correction here is something depending on x and y is completely determined by the algebra.
It looks like the action of some correspondences, or maybe, hold on,
right, yeah.
maybe Hecke algebra of the category of torsion sheaves of.
Yes. Now I will say a few words. I'm almost out of time. So what is important here is that, well, I think that this algebra action is very useful, and even if you're not interested in P equals W conjecture, it should, I expect that it gives you a lot of interesting information about the cohomology ring. But the way we apply it to the P equals W is the following. So the main application is that the operators D20, so observation is that D20 and there is one D11. Well, I already, sorry. This. To form SL2 triple, and this is somehow that implies that P equals W conjecture. So I claim that there is this unique filtration which satisfies this property too for these operators because they form an SL2T. So now I will make some remarks. So the operator D02(1), which is psi 2, 1. This is an element in H2, and is a relatively ample class. So this SO2 implies the relative populations. Think that so there is so the whole cohomology ring becomes has now SO2 action, and this is sort of raising operators, a multiplication by this tautological class, and lowering operators of some more mysterious operators, d to the 1. So, the second observation is that once you have SO2 action, you can also integrate it to get a Lie group SO2 action. Even you can get GL2 action. And there is this matrix. I mean, you can take 0, 1, minus 1, 0, or because this matrix here gives the symmetry, provides the symmetry between the part D0n and Dn. Okay. Third thing is that the algebra generated by this D and 0 is commutative. It's clear from the commutation relation, and is isomorphic. Is isomorphic to the algebra of Hecke operators. After some completion. So,
what do you mean algebra of Hecke operators on what?
so you wait, sorry, this so when you say completion, it means you're allowing some kind of infinite sums of operators, and they make sense provided your infinite sum is eventually 0. So in this sense, this is a completion. So the point is that also how does the construction works? The idea of construction is that you have okay, maybe next page. So consider, so we get operators by taking the Hecke diagram. So, and this is like we have M Dolbo for rank R and D. R equals 1. And there's some kernel here and some line bundle L, and there is like phi 1, phi 2. We take phi 1 upper star, C1L, some power, by 2 both star in a slightly modified situation. But idea is that suppose you constructed some operators, then these operators are basically unipotent up to constants. And you have to pass to the corresponding nilpotent operators. And these are our D0, DMN. So well, topologically important. And that's how we basically construct the.
You wrote DM0 on the other page. Do you consider all possible DMN?
Yeah. In fact, it's for all possible DMN. So N corresponds to this N here. So the situation is slightly more complicated because we have to take these operators, put them in some algebra, compute that algebra, and then extract our nilpotent operators as some kind of coefficient of expansions of those operators in the other algebra. But it would maybe take over much more time to explain. So let's maybe I stop now and then I will try to answer questions.
Yeah, there are many questions. First, let's start from the end. Actually, even by looking at the notation, you know, there was this work by Schiffmann and Vassero about the action of W algebras on the cohomology of the moduli space of instantons, yeah. And basically, they also constructed some algebra of Hecke operators acting on those cohomology, and that algebra came not from vector fields on C square, not from Hamiltonian vector fields, but actually from the cohomology. That's kind of two-dimensional version of our cohomological whole algebra with Maxim. So, and the reason why that cohomology appears, it wasn't clear at the time, so it was really a trick. But later, after Nekrasov generalized the story to this Nekrasov instantons, it became clear why one should consider cohomology of cohomological whole algebra of C square. So what's the reason for the appearance of this H2 in the story?
Yeah, let me explain this picture. So if you take, so I hope you, it's okay if I consider some situation which is completely different, but like what you're saying, like in this, like about
yeah, that's fine.
So if you take S, let's say compact surface, compact algebraic surface, and then maybe take Hilbert scheme of S and Hilbert scheme and take the homology and take the direct sum and then there is some algebra from algebra X there. So we can see, for me, for instance, with lens paper in this context. But it's a deformation.
Yeah, isn't it just Nakajima?
Yeah, Nakajima operators. So you have Nakajima operators plus tautological classes. And then computed how the tautological classes interact with Nakajima operators. So this algebra is a deformation of, let's call it HC star times C times the cohomology ring of the surface, where this is the Lie algebra. Well, so some algebra, the universal enveloping algebra of this Lie algebra.
I do not understand the notation. I do not understand the notation. What is HC star?
That's what I'm saying.
Ah, okay.
Hamiltonian vector fields on C star times C, which is a tangent bundle of C star. Okay, so that's one piece of the picture. And the problem with this is that there is no SL2. And the reason is that there is no SL2 is clear because C star times C is not symmetric. So to get SL2, there are two ways. To get some SL2, there are two ways. One way would be to replace C by C star. And to get some, and this corresponds in geometry, means pass from cohomology of your moduli space to the K theory of the moduli space. And this is, I think, what Andrei Negut is trying to do. And then I guess, I don't know if he has results in this direction. If he can prove that there exists this algebra action and so on and so on. And other way, what we are using, that's what we do. So we replace C star by C. Star by C. And that means that you should somehow write these Nakajima operators QK. You should write QK is the sum Tn over n factorial k to the n. So we see that right is it now it's a you have to take the sequence of Nakajima operators and consider them as a function of k. So view qk as a function of k. In our situation, the algebra we get is not deformed, is not a deformation of this Lie algebra. It is just this Lie algebra on the nose. This is something that's specific to the case when the surface is the cotangent bundle of the curve. So undeformed, the relations are very simple, and that allows us to do this procedure, namely to view qk as a function of k. We can do it explicitly and extract the corresponding operators Pn, which will be our and 0. And then
from what you derive your d and 0, or is it just no, I do not see. D and 0 in these terms is what?
Is Pn.
It's Pn, okay.
Yeah, D and 0 is Pn. But in this expansion, which means that they are indirectly, they are in the same algebra basically as the Nakajima operators, but the relation is a bit complicated.
Mm-hmm. Yeah, so it's indeed very interesting. Okay, but probably there is some physical reason, I mean, physical in the sense of physics. There is probably, as in the Nakajima story, there was a reason which for Nakajima, then later, Nekrasov gave another reason. And okay, for what means no deformation?
In this deformation, the deformation depends basically on some cohomology classes which vanish. So deformation depends on classes in H4 of S and H6 S times. Therefore,
okay, which means that, okay.
It's very simple with the algebra, and that's, we can solve this.
H6, yes, okay. So, and in your story, there are no, these classes do not appear at all. And another question, it's more philosophical, probably. You know that these SL to triples, Lefschetz, hard Lefschetz, it's part of Hodge theory, not perverse theory, but conventional Hodge theory, yeah? And in a sense, what you are doing, you construct similar structures on the perverse side. So, and you also mentioned that it's part of non-abelian Hodge theory, the actual diffeomorphism. You didn't explain how it appears, but kind of naively one can think that you have a twistor family, which includes M. Dalbo kind of at the origin, at infinity with opposite complex structure, and this M. Betti in the middle, in between. Yeah, and so then your filtration, kind of the filtration which you have, for example, in the origin, it's kind of deformed, or in the other way around, the filtration which you have at the generic point, it degenerates to the filtration at, say, at 0. And so is it possible to spell this very naive idea using this SL to triples, just to look at the smooth compactification of M. Dalbo, take this SL to triples, blah, 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 take the filtration, and to see that it degenerates to what you construct as the twistor parameter goes to 0. kind of, you have two filtrations. Yeah, you just take one, it depends on the parameter somehow, and it degenerates kind of in a stupid way, maybe because the action of SL2 depends on the twistor parameter in such a way that it degenerates to the SL2 triple. I don't know. I mean, it's completely unjustified, but very naive question.
No, no, I didn't think about the twister story. And
yeah, because you see, somehow I have kind of a different point of view on P equal W, which maybe it's kind of, maybe in the end Ben Davison will prove something which I have in mind. It's not really about Dalbo and Betti, it's rather about twistor families of two-dimensional Calabi-Yau categories. So which means that there should be a similar statement. For example, instead of Higgs bundles, you can take coherent shifts on the cotangent bundle to your curve, which are pure, which are supported on curves on one, which have one-dimensional support. So it's something which sits on the cotangent bundle, which is a symplectic surface. Yeah, all right. And instead of this character variety, if you kind of do it carefully, you can look for a Fukaya category of more or less of the same cotangent bundle. Yeah, and so then whatever you have two categories with objects which have some geometric supports on the symplectic surface. So that's what I have in mind. That they did meet such generalization. So like, of course, the conjecture. And you can say what is P equal W, but without your nice description, I don't know what is it. But at least you can ask a question in these terms. So then you see, so kind of, I'm not sure P equal W, it's something about Higgs bundles, although it experimentally was observed and conjectured for Higgs bundles. Maybe it's more general. Yeah.
Yeah, so it seems, well, at least for this moduli space of one-dimensional shifts.
Because your Hecke operators, it's
at least we can probably compute this zero-dimensional Koha action.
And zero-dimensional Koha, how does it appear in your story, or is it kind of appears in the essential way, or you just have these Hecke operators and this is all what you need? I mean, do you really need this?
So we don't need that statement, but we think of this algebra generated by these operators as a zero-dimensional Koha. And in another paper, we are supposed to prove it.
Okay, yeah. I remember when I looked at your paper first time, you referred to some other paper where all technical details should be proved. Maybe not all,
paper
but
is self-contained, but if you want this more abstract statements about the relationship to Koha, then you need another paper.
Yeah, and you okay, and but what is important for me that it's something about surfaces, like in your story. It's essential that it's two-dimensional Calabi-Yau, not three-dimensional Calabi-Yau. Okay. More questions?
Now ask, can you go back to this using the SL2 triple, using this pi star L to give a filtration, and then you have the eta power giving the duality on this. Yeah, that's probably even earlier.
There was this
Before this slide, I believe, when you were defining the filtration on the cohomology, defining the perverse sheaves, or yes, in this part.
Perverse filtration.
Yeah.
Yes.
So I want to ask you about this eta, which is defining at the bottom of the slides, eta k. Is this somehow depending on this L, which is giving the important part of the SL2 triple? So is this eta some sort of the var group elements? Eta k.
Eta. So the eta is in H2 of the moduli space.
No, it cannot be Weil group element because it's nilpotent.
Eta is also nilpotent.
Well,
eta to the k is the isomorphism, which is setting to the negative from the negative components.
Yeah, but it's like a power, like if you have an irreducible representation of SL2, it maps, the decreasing or whatever operator, it changes.
That's what the pi inverse L, pi star L was
but
doing.
They are both. They are both.
The eta is also nilpotent in this case.
Yeah, they are nilpotent because of H2.
Okay.
You want a Weil group element. Maybe so the exponentials of this.
Yeah, when you complete to the action of the group.
So there is a. But if you go to some parabolic story, then you can have then there are these elements in H2 of M. They're like psi. Eta is psi2 of 1.
Oh, eta is also on this second.
But you can take psi1 of this parabolic. So you think that this is a parabolic point. And you can think about it as you have.
Okay, so that's something quite different from what I was thinking. Well, thank you.
Then these are, if you take exponentials, you should get a fine Weil group action. And there is another copy, and then you get double a fine kind of algebraic thing, but it's not deformed. Very much simpler. Computer.
Okay.
Well, thank you.
Yeah, thank you. Okay, so let's thank Anton for the very, very interesting and clarifying talk. It's really great. Thank you.
Thank you.
And this is it for today.